All right, so coming back into it, one of the dangers of doing sort of both dot product and cross product stuff in the same day in the same class is that there's always a danger that they get confused a little bit. So I don't know, whatever we need to do, hopefully that 5-minute break gave you a chance to kind of refresh your brain and wash the dot product stuff out of it for just a minute. Not that we're going to abandon it altogether today, but that we really want to shift gears and talk about using a different kind of product of vectors to measure different kinds of quantities of geometric interest. So the dot product gave us information about lengths of vectors, magnitudes, as well as about angles in between vectors. The cross product is going to let us go one step higher and think about areas. So what I want to do is first talk about a construct that our textbook does not, which I call the scalar cross product. I think this is a really useful way for us to think about how the dot product carries information about angles. But there's also one other thing that the dot product carries interesting information about, and it's called orientation. The dot product is going to be able to tell us, for example, whether or not we have a right-handed or a left-handed coordinate system. We talked a little bit about that in our first class. And so it's the difference between right-handedness and left-handedness. Biologists call it chirality. That difference between left-handedness and right-handedness is also something that the cross product is going to equip us to investigate. So I'll talk a little bit about the scalar cross product just to get us motivated. And then when we shift into the activities from the book, we're going to be dealing with the vector cross product instead. So let's just get started by sort of taking a tour through what I call the scalar cross product. So my definition of what the scalar cross product is. So this is something that takes two vectors from two dimensions and produces a scalar. That's why I call it a scalar cross product. And the idea is that the scalar cross product is going to tell me the area of the parallelogram that is spanned or formed by the two vectors v and w. We can use sort of basic geometry to figure out that that area is the product of the magnitudes of v and w, so the lengths of those two sides of the parallelogram, multiplied by the sine of the angle that those two vectors make with one another. And so we're kind of starting here with the geometric definition of the cross product, which is where we ended with dot product. With cross product, we're going to kind of start with the geometry. But the problem with having a sine here instead of a cosine, I mean, it seems like a problem when we first think about it, is that opens up the possibility for this quantity to be negative, right? Just like with cosine, the cosine could be negative. The cosine was negative for obtuse angles. Meanwhile, the sine of an angle is not negative for acute angles or for obtuse angles, but the sine becomes negative when the angle between my vectors passes 180 degrees. So positive, 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 suddenly negative, right? And so because of that possibility, this quantity is not only going to measure area, it's going to measure assigned area. Because it might be possible that if I measure this angle from v to w, which in this definition we're measuring in a counterclockwise fashion, that angle measure could be more than 180 degrees, right? If it takes me more than that many degrees to get from v around to w. So that's the geometric definition. But the good news is that, again, sort of using the law of sines from geometry, trigonometry, we can find out that if you give me two vectors in two space, that area of that parallelogram is nothing more than the first component of the first vector multiplied by the second component of the second, minus the opposite, the second component of the first multiplied by the first component of the second. Those of you who are taking linear algebra with me this summer will recognize this later on as being a determinant of a 2x2 matrix. So if I put the vectors v1, v2, and w1, w2, if I just stand them up in columns next to each other, then I get this quantity just by taking the product on the diagonal, v1 times w2, subtract the product on the other diagonal, w1 times v2. So v1 times w2 minus w1 times v2. And casting it as a determinant is actually what gives all of the cross products, any cross product that we can talk about, its important algebraic properties. Those include linearity. So if I take a vector that's twice as long, then the cross product is going to be twice as large because the parallelogram is twice as much area. And it's also anti-symmetric. Right? If I swap v with w, the dot product doesn't care. The dot product was symmetric. The cross product, meanwhile, is anti-symmetric. So if I swap v with w, I'm going to change the sign, S-I-G-N, sign, of the value of the cross product. It's going to go from positive to negative or vice versa if I trade places with these two vectors. That's what determinants do. That's also what cross products do. So here's the geometric idea behind what this scalar cross product is measuring. So it is measuring the area of the parallelogram that's spanned by V and W, but it is also giving us information about the orientation of that parallelogram. So in the case where the angle, the counterclockwise angle from V to W is an acute angle like this one, then we're going to get a scalar cross product that is just plain positive, right? And it coincides with the area of this parallelogram. And so nothing really changes if I make that angle into an obtuse angle as well, right? That this obtuse angle is still going to have a positive SINE sign, right? And that gives our scalar cross product also a positive sign that coincides with the area of the parallelogram. And so where things get interesting is if I bend this vector past 180 degrees over to here, for example, right? If I have the vector over here, now the counterclockwise angle measured from V to W covers more than 180 degrees. That makes the sign of that angle negative, and it makes the scalar cross product of these two vectors negative as well. So the area of this parallelogram is always non-negative because it's an area in geometry, but the scalar cross product is the opposite of that area. And so one of the ways that we can think about when a scalar cross product is positive versus when a scalar cross product is negative is we can think about it, as I promised, in terms of handedness and orientation. So one way to think about when a scalar cross product is positive, it's going to be positive when, if I put my right hand index finger in the direction of the first vector V and my middle finger in the direction of the second vector W, then my thumb is going to be pointing out of the paper that I have in front of me. It's going to be pointing straight at my face, right? So those are the cases in which we have a positive orientation to the parallelogram, that we have an angle of less than 180 degrees when I start at V and measure counterclockwise to W, that I can put my hand down, my right hand down on the page with my index finger on V and my middle finger on W, and my thumb is pointing upwards off the table at that point. And so it's kind of pointing in the positive z-axis direction, except that we don't have a z-axis here yet. When we get to the vector cross product, we will. And so that changes if I interchange V with W, right? If I just swap their places, then I have to swap which finger I'm using to represent V and which one I'm using to represent W, and I have to turn my right hand over. And so that's why if I do that, then a negative cross product is going to result when my index finger, right hand index finger, goes in the V direction and middle finger goes in the W direction, and my thumb is forced to point down through the table rather than up at my face. That's going to be how we recognize a negatively oriented parallelogram. So this is the construct that I call scalar cross product. And one of the things that I would like for us to notice real quickly is, similar to the dot product, there are these extreme kind of cases that if I change the direction of my vectors without changing the lengths, right, then the largest value that the scalar cross product can have is the product of the magnitudes of V and W. So that was just like the dot product, right? The largest value it can have is just the two lengths multiplied together. When does it actually take that value, though? In order to make it take that value, I have to arrange it so that we're right at the top of that sine curve. And what angle are V and W making in this case where our scalar product is taking the largest value that it can take on? Well, here the angle between V and W when we are maximizing the scalar cross product is 90 degrees. So it's sort of the opposite of what we had with a dot product. The dot product was 0 when our vectors were perpendicular, but the cross product is going to be maximized. It's going to have its largest possible value when we have a right angle between those two. Because for two vectors of a given length, the way to make the parallelogram with the largest possible area is to make that parallelogram a rectangle, right? So that's why we're maximizing the area when we have a right angle between these two vectors. Now, when is the cross product going to give us a 0? It's going to do that when our parallelogram has 0 area. And the only way to make a parallelogram with 0 area is to pick two vectors that are parallel to one another. So parallelism is when the cross product becomes 0. Perpendicularism was when the dot product became 0. So this is why we kind of need both of these kinds of products in our arsenal of vector geometry, because dot product really specializes in sort of measuring how much two vectors are aligned. It's large when two vectors are aligned with one another, and it's small when the vectors are perpendicular. Meanwhile, the cross product does the opposite. The cross product is small when the vectors are aligned with one another, and it's the largest possible when the vectors are perpendicular to one another. So that's the sort of the beginning of motivation for a cross product. It carries those two kinds of information. It carries an area, so if you like, the absolute value of the scalar cross product tells me the area of the parallelogram that's formed by those two vectors. And the sign, SIGN, of the cross product tells me about the orientation of V with respect to W. That if it's a right-handed orientation, in other words, if my hand would point directly at my face, if I put my index finger and right index finger in the V direction and middle finger in the W direction, then we have a positive orientation. Whereas we have a negative orientation when the cross product has a negative sign attached to it. So when we amp this up into the vector cross product in 3 dimensions, what we're going to find out is that the magnitude of that vector cross product is still going to measure an area of the parallelogram formed by the vectors V and W. But instead of having a binary choice of directions between positive and negative, as the scalar cross product does, the vector cross product is going to have a direction which is a vector in 3 dimensions. And so there's a lot more different choices for which direction that vector cross product is going to face. But just like with the scalar cross product, we're going to use that right-hand rule to figure out what should the direction of that vector cross product be. So that's where we're going to go next, and this is where we pick up with the textbook once more.